So the first two are cis and trans isomers. This one I told you was the same as this one, except it was a flipped version. And the last one was a structural isomer because it was structurally different. Like in all of them, the CH3s were bonded on two separate carbon atoms. This one had a CH3, this one had a CH3, this one had a CH3, this one had a CH3. The direction of the CH3s was different. But this one is different. It's structurally different. It's a structural isomer. And when we talk about structural isomers, what that means is that the arrangement of the atoms is different. They're connected in a different way. These are not connected in different ways. The orientation or the direction of the bonds is different. That's it. So these were stereoisomers. This one was the same as the first one, while this one is a structural isomer. Is that clear? This thing.
Yes, sir.
Yeah.
In which pairs are the members stereoisomers of each other? So I think that's the are the first one stereoisomers of each other?
They are optical.
They're optical. Now remember, stereo has two types. One is optical and the other one is geometric. So
Yeah.
so this one is, they are optical isomers. All four groups are different and they are mirrored versions. Make sure they are mirrored versions. The Cl is pointing in this direction. The Cl is pointing on the in the other direction. So they are kind of mirrored versions. So they're basically optical isomers. That's correct. What about these two? Are they geometric cis-trans isomers or not?
No, sir.
Because this one is a cis version, right? And this one is also a cis version. So they're not isomers of each other. They're exactly the same thing. What they've done is they've just flipped it around, like left to right. If you just flip it around, put it up and put it the other way around, it looks exactly like this. So they're basically the same. They're not different. What about the last two? Are they stereoisomers, cis and trans, or not?
They're not.
No, sir.
They're structural isomers, because remember, in stereoisomers, they should be bonded in exactly the same way. So over here, both Br and Cl are bonded to the same carbon atom, but over here, the Br and Cl are bonded to different carbon atoms. So they are isomers, but they are structural isomers. So that one is also not stereo. So remember, make sure you know this difference. Stereoisomers, they would be connected in the same way, except the direction of the bonds is different. Structural isomers, they would be connected in different ways. Then you have, we can ignore that, just isomers. 1 second. So this one, how many chiral centers does this molecule have? So the first one, is that chiral?
Yes.
Yes.
What about the next one?
Yes.
Again, pretty much I think all of them are chiral, except for the last one. This one is not chiral, right? Because it's got two H's.
Yeah.
This one is chiral. Top is different, right is different, left, bottom is different, right? The middle one is also chiral because the top has a double bond O. So I think that's the answer is 4. The next one is, in which pair do isomers have identical boiling points? So which ones do you think have identical boiling points? And remember this. Remember this, that optical isomers, especially small molecules, if you have the board in front of us, I must have told you that, where's the optical isomer part. If we haven't discussed that, we did multiple cis-trans. I did talk about that, the difference between them. When we were talking about the difference between optical isomers, I told them they were very, very identical. Like almost everything was the same. So it was very hard to distinguish which one is which. The difference between optical isomers was that they rotate plane polarized monochromatic light, this thing, in clockwise direction, while the other one rotates the plane polarized monochromatic light in the opposite direction. That was the main difference. So otherwise, the differences are like almost imperceptible in optical isomers. There would be large differences in biological structures that are made out of it because biological structures are complex. So if the direction of the bonds is different, then the bigger structure that is formed, like if you're making a complex red blood cell or some complex structure, like a protein in your hair, if the direction of the bonds is different, the outcome would be different. The structure that would be formed would be slightly different. So in biology, it matters a lot, but small molecules, they're almost identical. Is that clear? So the answer to this one is that optical isomers, they kind of have, everything looks identical except for the variation in their melting and boiling points. But for bigger molecules, complex molecules having optical isomers, the overall structure could change a lot. Is that clear?
Yes, sir.
This one is, which one is both chiral and acidic? So I think there was a similar question. This one is carboxylic acid. This is also the last one. It's also chiral because this carbon over here, it's CH. I mean, if I draw this, it's CH and there's a OH branch, right? And then, I mean, this one over here, CH, OH, and then there's COOH, which is carboxylic acid. And the bottom part is CH2. And again, it's C double bond O, OH. So this is how the molecule looks, CHOH, that's CHOH. This carbon is chiral. If you focus on this carbon, that's chiral. Plus it's acidic as well because it's got a carboxylic acid group that's attached to it. TK, is this clear?
Sure, but it's also the same with the C.
Huh?
The option C. The carbon in the option C is also chiral and it also is attached by the carboxylic acid.
No, that's not attached to carboxylic acid because if you look at it, it's CH. The top side is CH2, CH2Br. And the bottom side is CH3, so that's the 3Hs. Now this thing over here, remember this, whenever you have two oxygens between carbon atoms, that is this thing. Two oxygens and there's an H. So that is an ester, that's not a carboxylic acid. So although it is chiral, this one is also chiral, this one, but it doesn't have a carboxylic acid. This carbon over here, all four sides are different. I mean, this side you have a double bond, this side you don't have a double bond. So all four sides around this carbon atom are different. This one doesn't even have a chiral, so that one is out of the question. Is that clear?
Yes, sir. Got it.
So then you have we did a similar, I think we did that previously. Okay, we've got this molecule, not the previous one. So this one is, yeah.
In the previous question, was that carbon chiral for part B?
This is chiral, yes.
It is, okay.
Because
of the double bond.
Yeah, if there had been no double bond, then these sides would have been identical, right?
Yes.
But because there's a double bond on this side, on the right side, so the molecule, I mean, this side looks different from the other side. So which is why it's basically considered different, right? Is that clear?
Yes, sir.
Because the next question we're going to do this again. It's like, if you look at this question, he's saying how many chiral centers. Now this one is difficult because it's skeletal formula, right? So make sure you know how to count the hydrogens because they don't draw hydrogens. These points are your carbon atoms. So how many chiral centers are present in this testosterone molecule? So the first one, let's talk about this one. Is this chiral or not? How many hydrogens would this have?
2.
It's already got 3 bonds, right?
Oh yeah, then it would have 1.
So it's going to have 1 H, right? So listen to this carefully. It's like, so this one, are all 4 sides different? Left side, you get something else. You get this thing. Right side, you get something different. This side, you got an H. The other side, you got an OH. So all 4 sides are different, right?
Yes, sir.
Yeah.
Yes, sir.
So I'm going to put a star over there. That's chiral. What about this carbon atom? How many hydrogens do you think are bonded to this one?
2.
2.
So that's not chiral, right? This one,
Yeah.
this one as well, it's already making 2 bonds. So this one has 2 hydrogens as well, right? So that is also not chiral, right? What about this carbon over here? Are there any hydrogens bonded to this?
No.
Because
No.
it's
No.
already, but is this chiral? Are all 4 sides different or not? This side you get this OH structure, this side you get this thing, this bottom side you get something like this, and top side is CH3. So all 4 sides, they look different, right? If you're standing on this carbon atom, all 4 sides are different.
Yes.
So bottom side this thing, left side is this thing, right side is you got an OH CH3. So that is also chiral, right? What about this one over here? Is this chiral?
Yes.
How many H's would this have?
One.
So this one will have 1 H, right? So all 4 sides are different. This, like, if you're standing over here, you start walking to this side, you see something else, right? You go to this side, you see something different. You go to the top, you see something different. So all 4 sides are different. This is not chiral because it's CH2. Clear? This is not chiral because it's CH2. Then focus on these two. Like, let's focus on this one. Is this chiral? How many H's would this have?
One.
So is this chiral? Are all 4 sides different? This side you got this. This side you get this thing. This side you get something like this. So all 4 sides are kind of different, right?
Yes.
Yes.
Yeah.
And I think the same applies to this one as well, right? That's also chiral.
Yes.
Top is different. This side is different. Over here, you're getting a CH3 thing, and there's going to be 1 H. Same, I think, as this one. This one is chiral, right?
Yes.
Yes.
Yeah.
This side, this side, this side, CH3. So they all kind of look different. Double bonded carbon atoms are not chiral, so these are out of the question. This is CH2, this is CH2, this is CH2, this is CH2, this is double bond. So that's also not chiral. So no other chiral carbon atom. So that's 3 plus 3, that's 6, right? Is that clear?
Yes.
Yes.
So that's 6 carbon atoms, right? Now the next one is so make sure you get this right, because that's slightly difficult. Now the next one is about the multiple geometric isomers, right? We talked about that there's this thing, and he's saying how many cis-trans isomer does this molecule have? First thing, is this symmetric or unsymmetric? Because I told you if it's unsymmetric, to kya formula tha? What was the formula if it's unsymmetric?
2 to the power of n.
And n is the number of double bonds that are forming cis-trans, right? So this is unsymmetric. You got a carboxylic acid. On the left side, you don't have a carboxylic acid. So it's unsymmetric, right? So anyways, is this double bond going to form cis-trans or not?
No.
Make sure, look at it carefully. It's like a double bond carbon atom, right? The carbon has an H. This carbon also has an H, right? So it's got an H. This carbon also has an H, right? CH, right? What other thing is attached to it? There's another carbon chain that's attached. You got CH2 and so on, right? So this is also CH, and then there's CH2s, a bunch of CH2s, 4 of them attached. I mean, there are 4 of them, CH2, 4. So, and then the molecule continues, right? So you had a double bond carbon atom, and you got an H, So is this, which version is this?
Yes.
So
Cis.
this one is cis, and there's going to be another version which is going to be trans, where the H is pointing downwards. So this is chiral. If you like expand the structure, the carbon only has 1 H, and the other thing that the carbon is bonded to is to another carbon chain. This carbon also has an H, and the other thing that's bonded to is this carbon chain. So this is geometric, cis and trans, right? What about this next one? Is this going to be geometric?
No.
What's the difference between this and this? This is
Go
exactly,
ahead.
this is, it's the same. It's CH. I mean, one side it's CH, double bond. Then the other side is also C with an H, right? And then you have a carbon chain. The other thing that the carbon is bonded to is CH2. The other thing the carbon is bonded to is a CH2, is a carbon chain. So that one is also going to be cis and trans, right? And this one is exactly the same. It's cis. It's going to have cis and trans. Basically, what you should look for is when you get confused when you see the condensed formula, right? So when I draw this thing, right, CH3, right? So make sure when you see this, the carbon has an H, but it only has one H. That means the other group must be different, right? Like carbon, you know, the double bonded carbon atom has an H, but there's only one H. What's on the other side? On the other side, it's the CH3, right? This side as well, carbon has an H, but there's only one of them. So the other side must be different. It's got, the other side is CH3. If there had been two H's, then this should have been CH2, that's it. And there should be no carbon chain next to it. Is that clear?
Yes.
Yes.
So what do you get? 2 to the power 3. What's 2 to the power 3? That's going to give you, I mean, the 3 cis trans, right? So it's going to be 2 to the power. So that's 1, 2, and 3 double bonds. So 2 to the power 3 is
8.
8. Okay, is this clear?
Yes.
Yes, sir.
So then,
Sir, a question.
yeah.
I was going to ask, you can like work through this using the formula, but what if you didn't know the formula? How would you do it?
Then you would have to do all the combinations. Like the first one can be cis, the second one can be cis, this third one could also be. You just keep making the combinations.
Oh, okay.
I mean, for 3, you would have to make 8 combinations, and obviously, you would miss a couple of combinations. Like you can't.
All right, sir.
So you would need the formula. It's without the formula, it would be, for 4 it would be easy, but even then you might miss one combination.
Okay, sir.
So next one is a similar question. He's asking about chiral centers marked. How many other chiral centers? So very quickly, first one, this one, C with 2 H's, not chiral. CO, that's although they didn't show this, but there's a double bond here because look at this, it's carbon, carbon. So there must be a double bond because carbon makes 4 bonds, right? Is that clear?
Yes.
I say this one, is this chiral, the one that I'm marking over here? Is this chiral, this one?
Yes.
The top is different, the OH is different, or this,
Yes.
so all 4 sides are different, right? This is C. How many H's with this one? 2, right?
2.
Do you get it? So
2.
that's not chiral. 2 H's, that's not chiral. They've already marked these ones. Is this chiral, this one?
Yes.
Do you get that is chiral because all 4 sides are different? This is CH2, right? This is double bond, so not chiral. Move to CH2, double bonds, not chiral. What about this one? Is this chiral?
Yes.
So all 4 sides are different. Another double bond, CH2, so that's not chiral. So there are 3 more. I mean, there was no other option apart from this. So is this clear?
Yes, sir.
Yes.
Yes, sir.
So which compound exhibits both cis trans and optical? So is this one, now you know how to, is this cis trans or not?
Yes.
No.
The double bond?
It
Two
is.
there's only one H attached, right, on each carbon atom. So that means the other side must be different. It's CH2, CH3, that's the other side. On the right side. And on the left side, there's only one H attached to this carbon atom. What's the other side? That's CH3. So there's going to be cis and trans versions of this. This is cis. Is that clear?
Yes, sir.
This is not chiral because see, carbon, both sides are H's, right? So that's not chiral. Sorry, not chiral, not geometric. no cis trans. Is that clear?
Yep.
Yes, sir.
Yes.
So what about this one? Is this symmetric?
Yes.
Yes.
Okay, so again, focus on the double bond. The BRs attached on both carbon atoms with the double bond. So there's one BR over here, there's another BR over here. And there's only one BR. So that means that automatically means the other side must be different. It's over here it's CH3. And over there it's the carbon that's making the double bond. The other side would be CH3.
It's optical as well.
How is it optical? All four groups must be different. These two carbons are out of the question. They can't be optical, right? What about this carbon atom? This is 3 hydrogens. This is 3 hydrogens. So you can't be optically. Kya tha? You need 4 different. You needed 4 different groups, right?
Okay.
Or this is also not optical. ये जो पहला वाला था ना, ये पहला वाला था ना. This one is the first one. So both of them are geometric, but I mean they are cis trans, but they're not optical because double bond wale carbon to वैसे निकल गए optical में से. They're not anything that's got double bonds can't be optical. 2 H's, 3 H's, 3 H's can't be optical. It's probably then the last one. Is this geometric or not? Okay, you got a double bond. Both of them CH and CH, right? The end one over here, it's CH and BR as well. The other side is CHBr. So CHBr followed by CH2. So C with 2 H's and followed by CH3. C with 3 H's. So this is cis trans side, but is this optical as well, this molecule or not? Is it a chiral carbon atom?
No.
Yes.
Yes.
ये वाला जो है, this is chiral. I mean, this side is making geometric isomers, but there is a chiral carbon as well, because all 4 sides are different. So around this carbon atom, there's going to be mirror images. There's going to be 2 versions of this, 2 different shapes. The molecule will have 2 different shapes around this carbon atom. Clear, Aisha?
Yes, sir.
So the answer for this one is D. And what is the molecular form? We can ignore that for now. Any other? Yeah, he's saying how many structural isomers? Only structural, no cis trans, no optical, only structural. C3H5Cl3. So C3H5 and Cl3, right? So this is going to be slightly difficult because you would have to make all the combinations. So basically, I'm so only structural. So what I'm going to do is I'm just going to rearrange the CLs and see. I can't change the carbon chain. Only positional isomers are possible because 3 carbon atoms, they would always be in a line. So I can't change the carbon chain. So I can only change the position of the CL. So either all 3 CLs are at one end. These are the most difficult because there's a very bright chance you might leave one of them. So, or you can have 2 CLs on one end, 1 CL over here in the middle. Baki sare H hai. Or what you can have is you can have 2 CLs at one end and you can have the other CL at the other end, right? Here, what else? You can have 2 CLs in the middle side, right? And there's 1 CL on, and these are all your rest of the 5 hydrogen atoms, okay? So any other combinations? I can have one more. That's one very obvious one that I
One
missed.
CL on each carbon.
So 1 CL on each of the carbon atoms, right? And the rest is H atoms. So that's we've already reached 5. Is there a 6th one or not? 3 CLs on 1 carbon atom, 2 CLs on one end, 1 CL in the middle, 2 CLs on one end, 1 CL on the other side. 2 CLs in the middle, 1 CL at one end, right? And it doesn't matter, it's this end or that end, it's just a flipped around version of the same molecule. Or we can have 1 CL on each one of them. Is there any other version in which I can arrange the CLs? I mean, I think they're not, but I might be wrong. Is there another possibility?
No, sir, I don't think so.
So that's, I think, about it. It's going to be 5 different ways in which I can arrange this molecule, 3CLs. And just be careful about drawing flipped around versions. Like if I draw this one, like 3CLs on this end, right? That's not a new thing. It's the same thing. It's just a flipped around version of the same thing. So be careful about structural isomers when you're making them, that you're not drawing just a rotated or a twisted around version of the same molecule. It has to be a different arrangement. Okay, is this clear?
Yes, sir.
So,
Yes, sir.
which of the compounds shown have chiral carbon atom? What are the first one? Is this chiral? This one? I mean, it's going to have
No.
one. It's not going to be chiral. Why? Because both sides are exactly the same.
Same.
So what about this carbon atom? This has got an H. Is this chiral?
Yes.
Yes.
Because this side looks different. This, I mean, if you're standing on this carbon atom, this side looks different because there's an OH. Obviously, all 4 sides are different. And this one is also chiral because it's going to have one H, right? And if you're standing on this carbon atom, all 4 sides would look different to you. This has got a branch. This one has no branches. This one is HOH. Same goes for this one. Is this chiral?
Yes.
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 Okay, and this one would also be chiral, right?
Yes.
The other ones are not. CH2, 2 H's, 2 H's, 2 H's. So that's not chiral. What about this one?
It is.
Yes.
Okay, so that is, okay, there's going to be one H. This side is different. This side looks different. The CH3 is different. The H is different. So all 4 sides kind of look different when you're standing on this carbon atom. So anyways, that's this one is not going to be, it's got a double bond, so that's not. So 2, 3, and 4. The first one was not. That wasn't chiral. So 2, 3, and 4. And you've got this molecule. So he's saying, now this
Sir,
one,
a question.
yes.
Say in the 4th one, if the double bond oxygen, right, was on the left carbon, then it wouldn't be considered a chiral carbon, right?
Yes, because then if it had been on this one, right, then the 2 sides would be exactly the same. Like, I mean, if you go from this side, you go from this side. Like if somebody is standing on this carbon atom, he would see the same thing from this side. He would see the exact same thing from this side as well. And that would not make it chiral. Is that clear?
Yes, sir. Thank you.
Acha, then this one. Now this one is there's 2-methylpropene C4H8. And he's saying in addition to 2-methylpropene, there are X other isomers, structural or otherwise. So he's talking about all of them, stereoisomers, which contain, what is the value of X? So apart from this, in addition to this, there are X other. So you're not going to count this one. So 4 carbon atoms. The one that he has drawn is this one. I'm going to look at the molecule without the, I mean, because it's just 4 carbon atoms, right? So what other way can I arrange this? I mean, I've just removed all the hydrogens just to see the molecule clearly. It's carbons and there's double bond carbon. So what can I have? I can have 4 carbon atoms in a straight line, right? And put a double bond there, right?
Yes.
Or I can have the double bond in the middle, right?
Yes.
So that is the only, I mean, this is the only branch structure I can make. I can change the position of the double bond, but it would be the same thing, right? It wouldn't be any different. So the branched structure is only this one. That's the straight chain structure, 4 carbon atoms. Which one do you think is also going to form this otherwise, like geometric isomers? I mean, is this one making geometric isomers, the one that they have already drawn? Is this going to be?
No.
No.
That's not.
No.
What
It's
about?
gonna be the 3rd one.
Acha, theek hai. This one is not because there's going to be 2 H's. That's the same thing. You switch it around, it still remains exactly the same. So the third one is going to have this is H, and there would be 3 H's with this one. So you got a double bond, and both sides are different. So it's going to have the third one is going to have 2 versions. It's going to be cis and trans. Remember, both of them would be counted differently. Like there's going to be a cis molecule, and there's going to be this other molecule that's going to be a trans molecule. So apart from this one, we're not going to count this. There are X other isomers. So that's 1 and 2 and 3. So the answer is 3. So apart from this, you got 1 of this, and there are 2 of these. There's a cis version and there's a trans version. Okay, is that clear?
Yes,
sir.
Yeah.
So what else? No, that's radical. Just a second. So this one is kind of. Should we do this or not? How many of these primary alcohols contain a chiral carbon atom? I'll just quickly explain. This one is slightly tricky, but we should do this. I'll just explain what primary alcohols are. Primary alcohols are, you got a carbon with an OH, and the carbon has 2 H's, right? And on one side there's a carbon chain. That's what a primary alcohol is. So that means if I have 5 carbon atoms, he says how many of these contain a chiral carbon atom. So it has to be, I have to make it chiral. But this is the primary requirement, that the alcohol must look like this. Like all the other things must be attached on this side. So this is the minimum requirement, that it has to be a primary alcohol, and you have to make it chiral as well. So I'm going to keep this. I'm going to draw the first one. Like I've got CH2 OH, and the rest of the molecule would be on this side. So I've got 4 carbon atoms left. So 4 carbon atoms. How can I make it chiral? What I can do is I can have H on one side. I can have a carbon on one side. And I can have, how many carbons? There are 5 total, right? So I can have 2 carbons on this side, right? The rest are all H atoms. This one will have 3 H's. So this one is chiral, right? So this one is chiral. And it's also a primary alcohol because it has this group. I mean, that was the condition. It has to be a primary alcohol. So whatever structure I make, it has to be, I want to figure how many of them could be chiral, or how many of these contain a chiral carbon atoms. That's one. Is there any other arrangement that's possible with 5 carbon atoms?
Bonding the carbon with the first group,
Over here?
with the first carbon, sorry.
This one? I mean, I can't.
Yeah.
The H over here, right?
Yeah.
I can't change this structure because I have to make it primary. So I'm going to do that. It's so this is CH2OH. For a primary alcohol, this has to be there. So anyway, so I'm bonding the carbon on the top. So so that's my 5 carbon atoms, but that would not make it chiral, right? Because because all 4 sides are going to be all 3 sides are going to be the same. So I think that's the only one that's possible. Like if you want to keep this structure in the molecule, then that's the only chiral carbon atom that's possible. Because if I take the carbon on this side as well, then I'll have 2 H's over here, right? Is that clear?
Yes, sir.
Yeah.
Yes.
So only one. Anyways, if you want to drop off, you can drop off. We'll just do a couple of more questions. I'll probably send the recording later, TK4. So again, this one, student X. Okay, TK. I'll send the recording. We'll just continue with the questions so that we have one recording which has all these geometric and all these questions done in that. So this one is
How long, by the way, sir?
probably just 5-10 minutes more.
Yeah, okay.
So student X claimed that 17 carbon atoms in the 4 rings all lie in the same plane. That's wrong. They can't lie in the same plane. Remember this. When you have carbon making single bonds, what's the shape around that carbon atom? Carbon making 4 bonds. What is the shape?
Tetrahedron.
Okay, that's tetrahedral. That's not lying in the same plane. I mean, this bond is coming out of the page. So it's not lying in the page. It's not lying in the plane. The dotted line is going into the page, right? So when carbon atoms make 4 bonds, it's tetrahedral and they can't lie in the same plane. Carbon कब lie करते हैं in the same plane when it's making double bonds. When it's making double bonds, तो fan shaped होता है. That's lying in the same plane at an angle of 120 degrees. But so apart from these 2 carbon atoms, none of them are lying in the same plane. And remember, even if it's tetrahedral, and if I want to show you the shape of cyclohexane molecular model, this is, I think, model. This one. So this clearly would show you that Kangi shape. So this one, you can see that all of them, all 4 carbon atoms are tetrahedral, right? They're all making 4 bonds. So they're not lying in the same plane. Koi upar hai, koi niche hai, theek hai, they're not lying in the same plane. This one is also probably pata nahi aa raha hai ki nahi aa raha. Well, so this is also a good example of a tetra, sorry. So they're not lying in the same plane because it's tetrahedral. Is that clear?
Yes, sir.
Yes, sir.
Acha, aur phir hai ki, so the first student is definitely wrong. Which of the students are correct? The first one is wrong. What about Y? He claims that the molecule displays cis-trans isomerism around the double bond. So there is a double bond, but remember that I gave you a condition that there's got to be a double bond, but it should not be cyclic, because you can't have geometric isomers in cyclic structures. Okay, you can't twist one side around, because if I want to twist this side, I would have to break the whole structure, right? And if I break the structure, then that's a structural isomer, not a geometric isomer.
So, sir, in a cyclic compound, you can't have a geometrical.
Because
isomer.
a geometric isomer was that you were not breaking bonds. You were just changing the direction of the bonds, right? Is that clear? So
Just changing the direction.
in a geometric isomer, the only thing that you were doing was changing the direction, right? This bond is over at the top. So in the geometric isomer, the other one, this bond should be facing downwards, right?
Bottom.
But
Yes, okay.
but you were not breaking bonds. Everything was connected in the same way. But over here, if I want to make a geometric isomer, I would have to break a bond. And
Yes, sir.
because there's no possibility that I can twist one side, right? And when I break a bond, then that's a structural isomer. That's not a stereoisomer. So B is the answer. Both of them they look incorrect, right? Ignore this. Which compound does not show cis-trans isomerism? So this is about naming. Does not. Pent-2-ene. Pent-2-ene means 5 carbon atoms, right? 2-ene means double bond on the second and third. And on the second, there's a methyl group, which means another carbon atom. Will this form geometric isomers, cis-trans?
Yes.
Look at this carbon atom. 2 sides must be different, right?
No, you said geometrical isomer, so can't you just make the carbon face down?
No, but they're both exactly the same. So it doesn't really, like if I draw it in the original shape, this side has a CH3, this side also has a CH3. So it doesn't matter if I switch this around, it looks exactly the same. I mean, the minimum condition for a double bond was, for a geometric isomer, was that the 2 sides must be different, right?
Okay.
So over here, the 2 sides are different, but both sides must have 2 sides different, right? So over here, the 2 sides, they are different, but not on this side. They're exactly the same. So the first one is not showing cis-trans. The rest ones are probably are. Like if I draw this one, it's pent-2-ene. So that's 1, 2, 3, 4, 5. 2-ene means double bond. And there's a methyl on the third one. So that means there's a carbon on the third one. So that's carbon with 3 H's, 2 H's, 3 H's. So this carbon has 2 sides that are different. This carbon would have an H and it would have a CH3. So this side would be different, this side would be different. So it will form cis trans, right?
Yes, sir.
Yes, sir.
So what about C4 dimethyl hextrine? So that's 1, 2, 3, 4, 5. Hex is 6, right? And it's 3, so that means double bond is on the third one. And it's 3-methyl, so methyl is on the third one, and 4-dimethyl, so that's another methyl. So both sides are different, like you can add in the H's. So around this double bond, both sides are different. This one is different, these two are different, right? Is that clear?
Yes, sir.
And pentoene would also 5 carbon atoms, and there's a double bond. So this one must have an H, this one must have an H. So this is CH2, CH3. So around the double bond, this side, these two sides are different. This one will have 3 H's, so these two sides are also different. So it's going to form geometric isomers, right? Is that clear? Only the first one did not, because it had
Yes.
it had 2 CH3. So the answer is A, it does not show. Right? Is that clear?
Yes, sir.
Yes.
Okay, so this one, how many isomers with the formula C5H10 have structures that involve pi bonding? So pi bonding means double bond. First one, 5 carbon atoms. That's again, this one would be slightly difficult. 5 carbon atoms, that's double bond, 1 position. Make a positional isomer, put the double bond somewhere else. I can't put the double bond over here, that would be the same thing, right? Then I can make a chain isomer. I can change the carbon chain and I can put the double bond over here, or I can put the double bond in the middle, or I can put the double bond right at the left side. So that's 3. Then there's going to be,
No, it's.
Catches?
I think it's the same, but it is not.
It's not, but if you look over here, I said this one would be the same. If I put the double bond over here, then it would be the same. Like if I instead of, I mean, this is single and this, I put the double bond over here. These two are exactly the same. Okay, whether the double bond is between these 2 carbon atoms or these 2 carbon atoms, the structure is exactly the same. Okay, you got a double bond carbon atom. So you got a double bond carbon atom, and that has 1 carbon atom and 2 carbon atoms on one side. You have a double bond carbon atom, and that carbon has 1 carbon atom and 2 carbon atoms on one side. So these two are exactly the same. I mean, they're connected in exactly the same way. But for twist way, now they're exactly the same. So what about 3 carbon atoms and 1 over here and 1 over here? The problem would now be I can't put a double bond anywhere. Okay, if I put a double bond, क्योंकि उसने कहा था शर्त ये है कि pi bond होना चाहिए, so there must be a double bond. So if I put a double bond, the carbon is now making 5 bonds, so it would be structurally incorrect. Is that clear?
Yes, sir.
Yes, sir.
So those are the only
So I
ones.
believe it's 5, yeah?
So that's 1, 2, 3, 4, 5. But he didn't talk about. We haven't done cis trans yet. We just use structural isomers. So which ones do you think are forming cis and trans? This is not, because there would be 2 H's with this, right? This one is not, because there are again 2 H's with this. This one is not because 2 sides are the same. This one is not because it's got 2 H's with it. This one over here has 1 H and 1 H. So this one is going to have cis and trans. Is that clear?
Yes,
So-
sir.
Yes, so it's 6 then.
So it's 6. I mean, this would be counted twice. There's a cis version and there's a trans version. So the answer would be 6. These questions are difficult. The other ones are kind of easy, but these ones where you have to make all of them, that you can easily miss one of them. So the questions like these are easy. वो जिसमें count करने थे ना chiral carbon atoms, they're kind of easy. Like del cis trans, that's easy. But when they ask you to draw all of them, that's kind of difficult. I mean, the question is not difficult.
Yes,
It's just that you can miss a couple of them. As anyways, is this how many chiral carbon atoms is this chiral?
Yeah.
Yes.
No.
So is this
No,
chiral?
no. So
Two H's, right? Is this chiral?
no. Yeah.
So this one
Yes.
is chiral, right?
Yes,
Cl,
sir.
H, this side is different. Is this chiral?
Yes.
Yes.
No, it's not. Okay. This side
What?
is the same, CH2Cl, and the bottom side is also CH2Cl.
Oh,
So that is not chiral. Okay? That was a trick. I mean, that most people would get this, would think this is chiral. This is not chiral. I said these are not chiral 2H's. This is not chiral 2H's. So there's only one chiral in this one, right? Clear?
yes, sir.
Yes, sir.
So what about how many isomeric esters have the formula? Hopefully everyone knows what an ester is. 4 carbon atom ester. An ester is this thing. It's got C double bond O and O. अच्छा यहाँ पे H हो सकता है, or you could have a carbon chain. But it has to be in the middle. The 2 oxygens must be between carbon atoms, right? So 4 carbon atoms. So what I can have is first one, double bond O and O, and I can have a carbon. That's an ester. That's an ester, right? I can change the position now. What I can do is I can have double bond O and carbons, 2 carbons on this side, right? Or I can change the position even more. I can have double bond O, and I can have 3 carbon atoms on this side, right? So I'm just moving the ester to the left. There's going to be one more because this one can be,
Sir,
yeah.
how did you make the second one? Because isn't the second one the same as the first one? Because
Nahin,
your second position.
See, it's 2 carbon atoms, but the 2 carbon atoms are attached to serial bond O, right? This one has 2 carbon atoms, but those 2 carbon atoms are attached to the other side.
Oh, okay.
So structurally they are different. And
Well
this
done.
one on the other hand has 3 carbon atoms. So this one I can convert it into a branch structure, like 3 carbon atoms, right? So I can have 3 carbon atoms like this as well, right? So that is also an ester, right? Is that clear?
Yes, sir.
Yes, sir.
I said, but the oxygens must be between the carbon atoms. So I can't shift this one to the right because then it would not be an ester. The 2 oxygens must be between carbon atoms. This was 1, the other one must be there. So that's, I think, 4. I think that's 4 because these 2 I can't rearrange. I can't rearrange this, but I can rearrange 3. So that would be 2 versions of this one. ठीक है, is that clear?
Yes, sir.
Plus, I don't think, I mean, there's no cis trans because there's no serial bond C, and there is no optical as well because this one has 2 CH3s, so it can't be optical. So all correct. It's which diagram shows the skill formula of 2-chloro? I mean, pentan 3-ol is 5 carbon atoms, right? It's the first one. 5 carbon atoms, that's pent, right? All means third. There's an OH on the third one. That's 1, 2, and so OH on the third one. And 2-chloro means that there's a Cl on the second one. Clear?
Yes, sir.
Yes, sir.
So what are the same for a pair of optical isomers? Optical isomers, everything is identical. The structural formula, the functional groups, the empirical formula, everything is identical. They're just mirrored versions, right?
All right.
So everything, even the physical and chemical properties are kind of similar. They're not similar for bigger structures, biological molecules, but for smaller molecules, even that would be similar. So this one is how many sigma? That's easy. That's another one. This one. An alkene has the formula CH3, this thing, and does not possess cis trans. So it should not be cis trans, right? So I'm going to draw this, the middle part, C double bond C. On one side, there's an H, right? I mean, this side, there's an H, and there's a CH3. This other side, there's an R. We don't know what R is. And you've got CH2 and CH3, right? Is this clear? Okay, double bond.
Yes, sir.
The way it should not form cis trans isomers. So this side is different, right? So should this side be the same or should it be different?
It should be different.
If it's different, then it will form cis trans, right?
Yes. Shouldn't two molecules be same?
He
Oh
says
yeah, yeah, you told us.
he said that it does not possess cis trans isomers. I mean, what was the condition for having cis trans isomers? That the two sides must be different on both sides, right?
Yeah.
Since he's saying it should not, then the two sides must be the same if it's not forming cis trans, right?
Yes.
So R must be the same as the bottom one. Like even if you flip it around, it should not be a different structure. It should be the same structure. It will not form cis
Right.
trans. So the answer is going to be D. It's going to be C2H5. R must be CH2, CH3. Aisha, clear baat?
Yes, sir.
तो it should not और बाकी क्या है कि इन्हें पहले क्या था पता नहीं कर लेते हैं इसको दोबारा पता नहीं I need this. I think is saved. How many chiral centers are there in one molecule of menthol? So this is kind of the same. It's this is one, this is another one, this is another one. The rest is CH2s, right? This bottom one is also not. It's also not chiral. What about? Not sure why this got saved. He's saying the following compounds are found in seaweed. Which compound would show both cis-trans isomerism and optical isomerism? So the answer would be, it's too messed up. Just a second. This will show cis-trans, right? If you see the double bond, two sides are different, and the two sides are different over here. Is that clear? They're going to show cis-trans isomerism, right?
Yes.
Yes, sir.
And for optical isomers, all four sides must be different. This carbon atom has all four sides different. There's a Cl, there's an H, there's a Br. This one is, I think, a Br. And at the bottom side, there's this entire thing. Is that clear?
Yes, sir.
Yes.
So that one, this one will not show cis-trans, right? What's wrong with this one? This one will not show, I mean, this carbon atom will not be optical because the two Brs are the same. These ones are double bonds, so they won't show optical. The last one, again, the two Brs are the same, so they would not show geometric isomers, cis-trans. Is that clear?
Yes, sir.
Yes.
So Baki, hopefully that's involving pi bonding, which compound exhibits stereoisomerism? I think it's the first one because it's CH3. Then there is C with an H. Then there is C with a Cl. Sorry. Let me draw this again. The first one. It's CH3. Then you have C with an H and Cl, right? And then you have another C with three H's, right? So this is not going to form optical isomers. Is that clear?
Yes.
Yes, sir.
अच्छा उसके बाद what about the next one? CH3, CH, Cl. So CH3, so CH3, C with an H and a Cl, right? Then you have CH2 and Cl. Will this form optical isomers or not? क्या होगा? Is this?
No, sir, it won't.
Look at the carbon. CH3 on one side, H on top, Cl at the bottom, and CH2Cl on the right side. Aren't all four sides different?
Yeah, it is different.
So it will form
Oh,
optical isomers, right?
okay.
The next one will not. It's CH3. Then it's so that's CH3. Then C with two Cls. So that's Cl on top, Cl at the bottom, and then there's another CH3. So that's C with three H's. So again, all four sides are not different, right? You will be Carlos. C with two H's and a Cl. The next one is C with two H's. So that's an H. Then you have C with two H's and a Cl. So this will not show optical isomers because वो दो H लगे हुए हैं उसके साथ. This one will not show optical isomers because again there are two H's bonded to it. The middle one will not show optical isomers because there are two H's bonded to that one as well. So it's only this one, the B one, that's the one. Is that clear?
Yes, sir.
Yes.
अच्छा बाकी आ जाते हैं
ठीक
कि including structural and CR isomers, how many isomers are there of C2H2Br2? So C2, H2 and Br2. I mean, I'm drawing the first one. There must be a double bond because the bonds are not getting completed. So that's one. दूसरी version क्या होगी? The other version would be that it would be double bond and the BRs would be on opposite ends, right? So these are the only two.
Yes, sir.
These are the only two arrangements that are possible. Which one will form cis and trans isomers?
The second one.
The second one, that's going to form cis and trans. So that's going to form cis and trans isomers. So that would so that's three. One this and two of these. So the answer is three. I said now this one, you've got two double bonds. Is this
So how
symmetric?
many questions left, by the way?
पता नहीं बस खत्म होने वाला है ये बस लास्ट कर लेते हैं.
Okay.
How many is this symmetric or unsymmetric?
Which one?
Symmetric.
This one is symmetric, right? You got two double bonds. Both of them are forming cis and trans isomers, right?
Yes, sir.
So so how many 2 per n would give you 4, right? लेकिन ये हमने किया था अभी. I told you that if you have a symmetric molecule, then what will happen is
This is work.
huh?
This won't work if you have a symmetric molecule.
There's going to be one. It would be
Both of-
it would be 3 instead. I mean, we did this one like then you'll open the notes. तो वहां पे ना भी नहीं, that's still loading.
Trans and trans is the same.
हाँ,
Then
क्यों-
cis is
हाँ, because you had cis trans, and you had trans cis, and then the last one was trans, right? So the thing was that these two were exactly the same.
Oh, all right.
तो बस ये था. बाकी
So could you use a formula such as 2 to the power of n minus n?
no, you can't really. I mean, you should. I mean, you should
Oh,
make the
okay.
combinations in that case. They'll probably not give you more than 2 double bonds.
All right.
We did this for 3 double bonds as well, but there's not
Yeah.
been a question with 3 double bonds yet.
Okay, sir.
For 3 double bonds, you had 2 to the 3 was 8, but in symmetric it was 6. ठीक है?
Yes.
I said the rest is all about counting. Again, this one is Chiral Centers. We did questions like this where you can go through them. This one is again 1 double bond, 2 double bonds, 3 double bonds. All of them are forming cis trans. So 2 to the 3, and it's unsymmetric. So that's going to be 8. I think that's a repeated. Yep, we're done. Maybe. Yeah, we did this one as well. So that's just a repetition. So we're done. We're done with this one is again counting all the Chiral Centers. You can do that. So we're done with these questions. Okay.
Sir,
चलो
have you sir?
हाँ जी ये मैंने
Have you
send
All right,
किया.
Allah Hafiz, sir.
Okay, Allah Hafiz. I'm sending this worksheet. ठीक है.
And sir, I'm getting trouble with time management.
नहीं किस टाइम पे?
I mean, no, not that time. I'm having difficulty managing my time according to the MCQs. I'm taking longer than.
नहीं वो
expected.
तो अभी छोड़ दो. अभी कोशिश करो कि असल में बताओ इशू क्या है. इशू ये है कि ये वाले जो MCQs है ना ये टाइम ज्यादा लेते हैं. ठीक है. तो उसमें बहुत सारे MCQs होंगे जो टाइम कम लेंगे. तो उन पे आप टाइम बचाओगे और फिर इन पे आप टाइम जाया करोगे. समझ आ रही बात? तो अगर आप अगर आप लेट्स से इसी के क्वेश्चंस कर रहे हो ना तो ये तो हमेशा ये टाइम लेता है. इसमें तो आपके टाइम बचेगा ही नहीं ना. लेकिन आप किसी और जगह टाइम बचाओगे जिस तरह अगर वो बिल्कुल स्ट्रेट फॉरवर्ड क्वेश्चंस भी आते हैं ना इनऑर्गेनिक के
Yes.
कि वो बता दो क्लोरीन का कलर क्या है तो बस वो स्ट्रेट फॉरवर्ड है. तो उधर आप टाइम बचाओ और फिर इस पे टाइम. तो वो जब पूरा पेपर करोगे ना तब आप देखना, ठीक है, पूरे पेपर में उधर टाइम का कितना मसला बन रहा है, ठीक है।
ठीक है, थैंक यू।
ओके, अल्लाह हाफिज।